I want to make sure everyone can hear me. Good. Okay, I guess that's a good thing. Okay, great. So just where we are, because apparently I auto sorted and I gave two of them the same number. We're starting with carbonyls, if you can catch up. So these are the relevant lectures. It's exactly what it says in the schedule, and that's what we started doing last week. And we'll move through this relatively quickly, and then we will move into carbon-carbon double bonds. If you started here, that's also okay, but we are covering this material. So as always, we can start by if there are any questions from anybody about any of the material in those lectures. Last class, we were starting to get started on these kind of reductions. There we go. Organized. It hasn't been asked yet. We have to. Can we do some examples? Yeah, we're going to. So we're going to start working through some of these, and I think I want to start talking about. We're going to talk about some more reductions, and then we're going to move into some oxidations. And again, we're going to be sort of thinking about how these work mechanistically. So again, this is a mechanism that we've drawn here with the hydride from lithium aluminum hydride attacking the carbonyl, making the single product. Now let's draw some neater ones. So let's say we have a different type of carbonyl. And let's say we have the same reagent we used last class, lithium aluminum hydride. We use THF, a solvent, 0 degrees, and again THF is that. It's a solvent. It does not participate in a reaction. It's just normally we don't grind up our starting materials with our reagents. We normally dissolve everything together. So if we do this, whenever you have a problem like this, there's a bunch, and let's say the question is provide the mechanism of the reaction, provide the product of the reaction. You can do this a few different ways, because you can provide, if you can see what the product's going to be, you can draw the product and then draw the mechanism. You can work through a mechanism to develop a product. Well, actually, those are our two ways. So we were talking about reducing agents last class and additions to carbonyls. And in the last example, we had the idea that this H-, which was nucleophilic, attacked this electrophilic carbon because it was part of a carbonyl. So again, all reactions normally involve stabilizing unstable things. And if I'm looking at this starting material over here on the left, or this reactant, it looks pretty stable. It's neutral. There's nothing all that weird about it. So this doesn't jump to me of what this is going to do. It's really going to depend on what the reactant, the reagents are. The reagent we have is this lithium aluminum hydride again. And again, when you see this, we sketched it on the last slide, but it's essentially H-. And it's nucleophilic, not basic H-. We're going to get into more detail on why that is on when we start talking about near the end of the class, actually. But fundamentally, it comes down to the idea that it's not completely ionic. The H minus is mediated by being attached to the aluminum. So it's not like a naked H minus. It's attached to the aluminum. It's not completely free. That decreases its reactivity a bit. So it's less likely to act like a base, and it's more likely to act like a nucleophile. So it's a source of H minus. So if we think about the pattern of what we saw in the last slide, we can draw in a lone pair on the H minus because that's what H minus is hydrogen with a lone pair. Try drawing the arrow, the first arrow, the first two arrows you need to draw. So use your nucleophile to attack your electrophile. Then this is your nucleophile. This whole molecule is your electrophile. We can say that the most positive center on the electrophile is the electrophilic. In this case, it's a carbon, with the electrophilic atom. And we know it's the most positive center on the whole thing because you can draw resonance structures and you can convince yourself that that C plus is where most of the positive charges on that molecule for the resonance structures. So if we have this happening, the arrows that we should draw are from the electrons on the nucleophile to the electrophilic carbon, and then we're going to break the carbon-oxygen double bond onto the oxygen. Why are we doing that? Because if we don't do that, that carbon's making 5 bonds. And so the carbon's going to break its weakest bond. And its weakest bond is a pi bond. Pi bonds are always the weakest bonds. Samara, can you jump into, I see there's another meeting. Can you jump into the other meeting and let them know that this should be in this meeting? Unless they're like meeting about other stuff.
Yeah, I can do that.
Thanks.
All right. All right, guys. So
So you're still in this meeting?
yeah, I am.
Okay. Oh, maybe she got started. Okay. So what we end up getting if we follow those arrows is we've now attached that H that we just added to that molecule. That's exactly the same pattern we saw in the last case, except there we only had a carbonyl. Here we have an ester. So why does that matter? Well, it matters because I think I mentioned this early on in the course. Oh, no, sorry, Samara, just there was another meeting. If you could just handle the other meeting. No, it's all good. Because there was I saw there actually is there's another meeting that's meeting now in my teams. And I think there might be people in that meeting. And they might be waiting for the course to start, but the course isn't in that meeting, it's in this meeting. So I don't know if you can pop out and join the other meeting that's not in class and tell them they should be in a class meeting. Thanks, Samara. Anyways, let's think about something here on the side. So if we have acetone, And if we treat it with water, what we end up able to get through a very similar mechanism to what we've been drawing we're going to come back to this mechanism in a moment, but let's just consider this for a moment, is we can add the oxygen as the nucleophile. Here, up here we had H minus, we've used C minus. We can add water, oxygen as the nucleophile. The arrows are the same, right? The arrows go from the electrons, they go to the carbon, we break the double bond, we make this. Now, all the time, I take my acetone squirt bottle and I mix water into it, and I do not get this. And that's because oxygen likes making double bonds with carbon. Because essentially what we have here is oxygen's making 2 bonds with carbon. Here, oxygen's making 2 bonds with carbon. But oxygen wants to make a double bond with carbon, not 2 single bonds with carbon. The reason for that is twofold. One is oxygen single bonds are stronger. If you just look at the bond strength, you think this would be preferred because the bonds are stronger. But in oxygen, the second bond, the pi bond in oxygen is still pretty good. It's not as good as a single bond, but it's pretty good. The bigger reason is entropy. Because although we've drawn over the arrow, the way we can think of this happening is you've got 2 molecules on the left-hand side of that arrow, and you've got 1 molecule on the right-hand side of that arrow. And if we're discussing entropy, just on purely entropic considerations, like pulling back all that stuff you've learned in first year, would we prefer to go left or right if you just think about entropy? Thanks, Emma. Remember, entropy is a measure of disorder. And the universe once becomes, yeah, left. Why, Faith? I agree with you. Or somebody else. Yeah, more molecule. Exactly. It's that freaking simple, right? You know, the heat death of the universe, all the matter is going to exist, but it's all going to exist as like hydrogen protons. Everything's going to dissolve into that, and everything's going to be equally spaced away, and everything will be, you know, not forming bonds because there's more chaos in there, and everything's mixed up. Making bonds makes order, and that costs you. It costs you entropy. So, in a lot of cases, we prefer dispersed, broken up things. So we're going to come back to this. Actually, it's in one of the next lectures up there that's on recorded, but we haven't talked about it too much. This is called a hydrate. I am never going to test you on what this is called, but those of you who want to look this stuff up and learn more about them, it's called a hydrate, and it's because you added water, which is hydrose. It's really unfortunate that hydrogen and like water are really because we'll often use hydrolysis is cleaving something with water. Hydrogenolysis is cleaving it with hydrogen. And that's really awkward, and I'm sorry about that. I think hydrogen got its name because it's kind of like water. It's in water, and so that's where it came from, but then they realized it wasn't water, and it's just everything's confusing. So if we think about this and we think, okay, so this lies to the left. Then what you think is, okay, well, I got this as my intermediate. But this is probably in equilibrium with something else. Okay, this is the first time we're breaking a bond. Okay, so what did we do here? Well, exactly like analogy with the lower one, we've gone from 1 molecule to 2 molecules, which is favorable. We've created a nice strong oxygen-carbon bond, but if we're going to double bond, but if we're going to do that, we have to break a bond to that carbon. Now, it could have picked any of those things to break, right? It could have lost O minus ethyl. In brackets, though, let's consider the other things we could have lost. We could have lost H minus, which is kind of where we started. That just takes all the way back to the beginning. Or we could have lost an ethyl minus. And remember, when ethyl minus is, it's CH2, CH3, and negative charge on the carbon. So if I have to choose between O minus, C minus, or H minus, which one am I going to form? Yeah, we're going to do a lot of hyperconjugation. Amanda, it's the click on the chapter 7 ones on the syllabus. Carbonyl chemistry, where the syllabus kind of got put backwards because it auto-ordered and 2 of them have the same number. I will update the syllabus online. Sorry, I'm checking to see which one it is because I am playing my YouTube video. It's called Carbonyl Chemistry. Lecture 17. So we skipped 13, 14, 15, and 16 for a moment. And we're starting with 17, 18, 19, and then we're going to go back to 13, 14, 15, 16. Yeah, so Noor, I just want to see what happens if we do it in this order. If you did the other order, we'll cover all that stuff too. You're right. So Noor said O minus. O minus is right. The other ones are less stable. You're going to favor O minus, so that's what you're going to make. That's the bond you're going to break. You're going to break the weakest bond. So here we have as a principle, a general principle of chemistry. You always make the strongest bond you can. You always break the weakest bond you can. And we see that very much alive here. Now, we've got an aldehyde. But if we have excess lithium aluminum hydride, so if we still have more of this stuff in here, because we just, took a bucket and piled it in without setting anything on fire, can that react with the carbonyl? So the question is, can this do more with chemistry or is this done? And in the last slide, we saw an aldehyde react with lithium aluminum hydride. Yeah, I like the question mark. It is, yes, we now have an aldehyde, we have lithium aluminum hydride. So it's going to keep going. And it's going to do, again, this is just 2 arrows. Nucleophile attacks the electrophilic carbon. The electrophilic carbon would then make 5 bonds if we didn't break a bond. So it breaks a bond. Which bond does it break? It breaks the weakest bond. Because again, think of it's got 4 bonds there. It can break any of them. Any of them is possible. So if it breaks either one of the ones to oxygen, it breaks the double bond because double bonds are always weaker than single bonds. And it will make an O minus. or we can make a C minus, or we can make an H minus. I'm going to make the O minus every single time under those situations. And so we've added this extra hydrogen. Now we've run out of carbonyls. So there can be more lithium aluminum hydride in there, but nothing funky is going to happen because we have run out of things to react with. So overall, what has happened here? It didn't matter if I started from, I use the same reagent. I have two different starting materials. And it didn't matter which one I started with, I get the same product. Got too many lines. And that's because the top one goes through the bottom one. The top product actually makes that carbonyl on its first reaction, and then it reacts further to the alcohol. So what we see here is really potent reduction. What if we want, I'm going to do another example on this, and we're going to see the other reagent that we're talking about in this course that does reductions, or two of them. We're going to see two reducing reagents, two oxidizing reagents. The other reducing reagent is called sodium borohydride. So let's just pause for a second and think, well, shit, that looks a lot like lithium aluminum hydride. Right? Boron is in the same column as aluminum. In both cases, we've got 4 hydrogens, and lithium and sodium are in the same column. So we have very similar kind of molecule. So you want to just take a second to try and draw what you think sodium borohydride looks like. It's going to look a lot like lithium aluminum hydride. That's going to react a lot the same way. Samantha, you're absolutely right. How did you know? We didn't. I would. So Samantha asked a really smart question. How did you know there was more lithium aluminum hydride to react? It doesn't make sense. If it doesn't state that there's only one mole of it, one equivalent, do we just assume there's more? I will always state if there's excess. But we're actually going to come back to that question because this question actually gets a little tricky if there is only one equivalent. So we're going to redo that question with one equivalent of lithium aluminum hydride. But anyways, let's just talk about this first for a moment. So try and draw sodium borohydride. So if you realize this is kind of one of those Lewis dot tricks the world plays on you, as it does. So you can't draw a Lewis structure. So we get, again, it's exactly the same thing. We've swapped the aluminum for the boron, and the sodium is now floating nearby instead of potassium, but you know, why isn't it potassium borohydride? I don't know. I think potassium borohydride is more flammable. And so it's nice when your stuff doesn't catch on fire. So what I'm going to show here is I'm just going to show a scheme, and then we are going to discuss it on the next page. And we're going to answer Samantha's question along the way too. And this time I'm just going to say excess of both. So if we look at the lithium aluminum hydride situation, we already discussed this. There's an ester and there's a ketone. And we saw lithium aluminum hydride reduce both. It reduced the ketone to an alcohol, and it reduced the ester to an alcohol via the aldehyde. It went ester, aldehyde, alcohol. So lithium aluminum hydride is going to generate that. Were the new hydrogens that came in from the hydride. There's one there, and there's two there. I'm going to talk about where this H came from in a moment, because it's not clear, because I've been drawing O minuses and it's of this nature. Where the hell did that come from? Why is this happening to me? We'll get to that in just a second. The secret is water. Now, if we do sodium borohydride, you don't know the answer to this because you can't, because that's why we're doing this. If any of you do, good for you. Good job on doing the readings and thinking about this. So sodium borohydride didn't touch the ester. It only reduced the ketone. And again, this hydrogen comes from okay. So with this information I've drawn here, which is the stronger reducing agent, the more reactive reducing agent? Lithium aluminum hydride or sodium borohydride? So aluminum or boron, which one's the stronger reducing agent? Perfect. So the aluminum is the stronger reducing agent. I think it's got to do with the lithium and the longer aluminum hydrogen bonds, because hydrogen doesn't make as good a bond with a third row element as a second row element. Details. The lithium aluminum hydride is stronger. Great. We're going to have a little table coming up. Sodium borohydride is weaker. So if it's weaker, why did it attack the ketone and not the ester? Why does a weaker one not touch the ester? Why does it attack the ketone? This can take you back to like lecture number 2 or 3. Okay, so the ketone's less oxidized. That's true. But so not very positive carbon on the ketone, Melitza. Nor I like your answer. It's definitely part of it. Resonance on ester makes it stronger. Let's be careful with what we mean by stronger in that case. But I think you've got it. So let's just think about the resonance structure of a ketone. It's only got one. Big positive charge on the carbonyl carbon. Whereas with an ester, and of course, if you're ranking resonance structures, you rank them that way. Hopefully. Why did I rank 2 above 3? Yeah, perfect, Samantha. Absolutely, Anna. You guys are absolutely right. So although we have the positive charge on the more electronegative atom, everybody's got their full octet. So suddenly if we're looking at this, we're going, the positive on the ketone is entirely on that carbon. The positive on the ester is kind of spread out over the oxygen and the carbon. So there's not as much localized positive charge, so it's not as electrophilic. So what we have is we have this pattern of oxidation. And I guess we can go all the way to the most oxidized thing you can get, which is carbon dioxide. By the way, find an efficient way to reduce carbon dioxide down to alcohol, methanol, and win a Nobel Prize. Because you could fix, climate change by reducing carbon dioxide directly from the atmosphere into methanol, which would be great. We'd have like tons and tons of methanol. Don't know what we'd do with all of that, but it wouldn't be a greenhouse gas. So this is like a direct climate relevant problem. What we've seen is lithium aluminum hydride is a strong enough reducing agent to do that. And sodium borohydride can't react with an ester. I'm lying a bit. It can. You just need to heat the crap out of it. But under normal conditions, it doesn't. You'll just react with, you won't touch esters. You'll just react with ketones and carbonyls. So one thing that we've left off, and let's think about this for a second, is I haven't drawn acid in there. I've drawn ester. I lied about there being 2 reducing agents. There's going to be a third one. R, any carbon chain. Doesn't matter. Okay. So if we treat this with lithium aluminum hydride, again, we can look at this carbonyl. And I said it wasn't basic. I said it was nucleophilic, but only if there's a really acidic proton around. The problem with this is that when it comes right down to it, and we're going to talk a lot about this in the next section of the course, is there's no real difference between a nucleophile and a base. The only thing a base is a nucleophile whose target nucleus is hydrogen. That's it. And that's a complete definition. So a nucleophile is something with excess electrons that wants to attack a nucleus. Hydrogen is a nucleus. Something that attacks hydrogen is a nucleophile, except we call it a base because it's a special nucleophile that attacks hydrogen. But bases are a subclass of nucleophiles. So in this case, this is what we actually see, is because we have such an acidic hydrogen, we can attack that. Now we have a problem. In the previous example where we had an O-, we had only two single bonds to oxygen. We were able to make a carbonyl, we were able to make an aldehyde. We can't do that now because we can draw resonance structures, but that's a very stable O-. The issue is that's not all that positive anymore because there's a big ass negative charge right next to it, right? So we don't have this positive carbon there anymore. So if you keep the lithium aluminum hydride cold, there's no reaction on the alcohol, on the acid. Nothing happens. That's why we wanted to use an ester, because we didn't have this crazy shit happening. We just attacked the carbon. So this does work if you heat it. Triangle means heat, normally to about 100 degrees. This will do the reduction. And you're maybe thinking, wow, this is getting really detailed, all these like conditional things. Yeah, I agree, and I'm sorry. But what we're doing is we're talking about a bunch of the concepts here. So again, this is not likely to react because suddenly this is not very positive because there's a huge negative charge there. So there's extra electrons on the molecule. We're less likely to attack there. So if we wanted to do that, we need to give it a lot of energy. And how do you give things energy? Well, you heat them. So if you heat this really hot, it will react. but you know, you don't often want to heat things in 100 degrees with lithium aluminum hydride. It tends to destroy molecules. So there is another reducing agent. We are not going to do the mechanism for it. You can look it up if you like. Similar, BH3, it's a borane, often done in THF. And you can do this cold. And this gives us the alcohol. There's 2 new hydrogens. So now what's really interesting is this works with nothing else but acids. If you try and take an aldehyde, which is very, very, very reactive, and you treat it with borane, no reaction. And again, I'm going to say, if you, that's curious, because this is harder to do than this. It's harder to reduce an acid than an aldehyde, but it reduces an acid and not an aldehyde. You are not responsible for this mechanism, but if you want to look it up because you're curious now, go ahead. It's kind of cool. It's just doesn't prove any points, and so I'm not going to go through it. So if we go back to our table of thingies, we can put in an acid. And the borane will take us from the acid down to the alcohol. So we've got kind of the reducing side. So we can go down, we can go to the right. How do we go to the left? So in these cases, what we've been doing is we've been adding H minus effectively to the carbon and breaking bonds to oxygen. If we want to go to the left, we're going to need to add oxygen to the carbon, and we're going to need to break bonds to hydrogen. Mechanistically, this is a lot more complicated. And for that reason, I'm going to show the reactions, but we're not going to talk about the mechanisms yet. We'll come back to the mechanisms. Again, if you want to, you can get ahead of us and take a look. It's actually in chapter 12, where we're going to come back to this. But what we're going to use is, let's say we have an alcohol. We can treat this with chromic acid. And sulfuric acid. And it will go to an acid. So just giving away the story a little bit. that oxygen comes from there. The other reagent, I'm only going to talk about one other oxidizing reagent, and again, we are going to come back to its mechanism much later in the course. Very closely, there are millions of oxidizing reagents. It's just, we'll save the rest for later courses. Got to save something. We're saving a lot. There's a lot of other stuff. Oops, you haven't seen this notation. You've seen THF, so I'll stick with that. This whole thing here is called PCC. If you type in PCC plus chemistry plus mechanism, you can learn about that. And what this does is this is just going to take us up to the aldehyde. Of course, if the molecule already has 2 bonds to carbon, we can't make an acid. We can only make an acid if this was already a primary, because we've got 2 hydrogens we can lose, so we can make 3 bonds to oxygen. Here we can't make an acid, so it doesn't matter what we use. We use the top reagent. It wants to go to an acid, but it can't because we can't break one of the carbon-carbon bonds. So what this whole thing is called is it's called the Jones reagent. Because it belongs to a guy named Jones. And it's chromic acid in sulfuric acid with water. So again, I'm just going to skip back to our graph of oxidations and reductions. I'm going to come back to these mechanisms, but they're much more complicated. So why am I trying to discuss something complicated when we're just starting to talk about mechanisms? Well, the reason I'm doing it is all this stuff shows up on MCATs, and if this is your organic chemistry course, it's probably a good idea that you've seen it. Otherwise, you're going to see this again in the next class, so it's not such a big deal. So this table here kind of covers our oxidation and reduction agents we're going to use in this class. We can go up and down this graph. We can go from more bonds to oxygen to less bonds to oxygen by reducing. And we can go up from fewer bonds to oxygen to more bonds to oxygen by oxidizing. What's interesting is it is really different. And as an exercise, I'm going to leave this because we're at the end of class. I'm going to leave this for the class. Let's say I wanted to do this, the thing in orange. So there are a bunch of options, but there's a way to do it using this chart. And actually the way to do it using this chart is the way that it gets done a lot. There are ways to do it directly, but they're specific and somewhat unreliable. So I'm going to leave this here. And this was sort of the second part of this. Next class, we're going to have any questions anyone might have about, well, we're going to do a few more additions to Boron. So if anyone has any questions about this and is thinking about that, we're going to add other things to carbonyls and see more examples. And we can go from there. But this graph here is kind of important. Okay, we need to get our GAs organized for marking and midterms, so I'm not sure when I'm going to get the grades back to you. I am going to hear lots and lots of whining and complaining from all of them because they're all going to say that they're spending all their time marking your labs, and I'm going to say you guys spend all your time doing your labs, and then you also manage to study for a midterm, so at least the GAs can do is mark a midterm here. But we're probably honestly looking at about 2 weeks to get the midterm marks back to you guys because everyone's busy. I hope there were no surprises on it. I'm interested to see what the grades come back as. Yeah, so skip 14, 15, and 16 for now. Start with 17 and 18. Well, yeah, that's a question. It's why does it always stop at the aldehyde? And do you stop at the aldehyde, or is there a different way to do this? Everything you need is on the graph. Yeah, so I think, so skip to the chapter 7 stuff on the syllabus. Oh, the last two last two reagents, the PCC, why does it always stop at the aldehyde? Why does the PCC not go up to the acid? Was that your question? We are going to talk about that. That is really dependent on the mechanism. I promise we'll get to that when we talk about E2 eliminations. But right now, I'd just be throwing way too much stuff at you. And when you see it, you go, oh, that makes so much sense. But right now, it would not make a lot of sense. You would start throwing things at me if we were in person. So I don't want to overwhelm you with too many complicated arrows. But I promise you'll have an answer to that question. I'll remind you how you had that question when we get to it. I also might have actually put into the lectures too. It's possible. It's possible it's in the videos. Okay. Have have a great day for everyone else too, and enjoy not having to study for a midterm right now, except I'm sure you have lots of other midterms because second year, that's all it is. It gets better. Second year is the worst. It's by far the worst year in a science undergrad degree.